All right, then let me begin. It seems that all technical problems have now been dealt with, so finally I can begin with my presentation. All right, hello everyone. Great that you're here. Over here, where I am in the Netherlands, it's now 3 o'clock in the afternoon, and good evening to you all there over in Manila. And yeah, I'm very pleased to meet you, and it's really nice to have this opportunity to talk to you this evening. So, before I start, let me tell you a little bit about me. I am Wiebe-Marten Wijnja. I have been a programmer and developer for about 10 years professionally, and have experience with many different languages. You can find me on the internet either as Wiebe-Marten or as the name QQWY. I really like making things that have some creativity or original thoughts behind it, and I try to give back to the community. I really like doing things with open source and creating interesting things, and thinking deep and brainstorming about possibilities. So for about 2 months now, I've also been a moderator at the Elixir forum. I'm very passionate about the language Elixir. I find it a very, very nice language, and in this talk I'm going to try to convince you that Elixir is a good tool for certain kinds of problems. I work at a company called Panache. Panache is a Dutch company, which you can find at panacheit.com. Panache is a company that does both consulting for informatics and programming things, as well as placement whenever someone needs more work, has too much work and not enough people. We can find you people that can help with your project. We use many different programming languages, and we've worked on many different projects, including one of the largest Dutch payment service providers. And Panache, the name in Dutch, means bold. We really like building things which we're really passionate about, things that are in a league of their own and have a top-notch quality. So, let me start with the actual talk. This talk is called A Winner is You, a practical introduction to concurrency in Elixir. I wanted to give this talk because concurrency is one of the major things that differentiates Elixir from other programming languages, and it's a really great thing to understand why this works, how Elixir tries to solve concurrency. And I want to give you a practical introduction so you can actually start thinking about problems and how you might solve them in Elixir. So first I'm going very quickly explain what kind of language Elixir is and why it is different from other programming languages. Then I'm going to talk more about concurrency and why it is important. And then how concurrency is actually a problem that is solved differently in Elixir than in other programming languages. Then I'm going to explain, to present to you a practical example to show you how to actually build something that is concurrent in Elixir. And finally, when we've built such a concurrent application, I want to show you how you can ensure that this application can then be made scalable and fault tolerant to ensure that it still works if part of it goes wrong. So this talk is meant to be understandable for anyone who has a basic understanding of programming languages. Rico, at the start of his talk, he already asked what kind of languages you people are using. And yeah, anyone who knows some other language or has programmed anything earlier will hopefully understand the things I'm talking about in this talk. So The idea is that my talk will take about 45 minutes. Right now we already have a bit of a delay because of some technical issues. I'm going to try my best to make all the things I want to tell you fit in this time, but concurrency really is a large subject. There's a lot of ground to cover. So I'm not going to go into every small detail, but I'm going to try to give you a general overview and give you an example of how you might make a practical application using this kind of thinking about applications and concurrency. I'm not going into all the syntax that is used in Elixir. There are some other guides that tell you how they work specifically, and Elixir prides itself with very good documentation, so it's really easy to get started when you actually want to code something. But I find it more important that you understand the thinking behind it than to understand the actual syntax that is being used. So I am going to give you an explanation, and I'm also, because that's of course always very interesting, show you that the things I'm showing you here in this talk actually work. So I will start up the Elixir shell halfway through this talk to show, well, what actually happens when we try this code out. So I'm not going to do any live coding because that would make this talk probably about twice as long, but I am going to show you that the examples that I'm presenting in this talk actually work. All right, so very short introduction of the language Elixir. Rico already introduced the language a little bit, but the most important aspect of Elixir is that it is a language that is built from the ground up to be concurrent and to be able to solve problems in a concurrent way. Elixir is dynamically typed, which means that it's very easy to get started using the language. It is built, it's immutable and a functional programming language. This really works very well together with the concurrency. It's kind of the reason that the concurrency works so well. And Elixir has been built on top of Erlang, which is also something that Rico already said. And the nice thing about this is that Erlang has been stable for a very long time. So we can be sure that Elixir has a very strong foundation and will work in most cases without any problems. All right, Elixir, one thing that Elixir really extends on upon Erlang is it has a syntax that is a lot easier to understand for people that are new to Elixir or new to programming in general. It's easier to switch over when you're used to the syntax from, well, basically any programming language except Prolog. So that's really nice. And also Elixir gives you the ability to define your own domain-specific languages. It has a very extensive macro system, which can enhance the language even further. Elixir really tries to be explicit instead of implicit, that some other languages do, which means that Elixir can let you do very cool things, but you will also at that time know exactly what is happening, and it's always you're always able to find out why something is happening. And this really happens because of its immutable and functional style. All right, but in the rest of this talk, I am going to go into more detail about the concurrent aspect of the language, which is arguably the most important part, and at least the part that is the most different from other programming languages. So let us first try to understand why concurrency is so important. And basically, as Rico's talk also already told you, the reason that is so important is speed. Concurrency means multiple things are happening at the same time and not just one thing as we're used to. The computers, modern computers, only get faster by adding more cores to the computer. The actual speed of computation hasn't been improved because we've reached the physical limit of what is technically possible. But it is possible to compute multiple things side by side at the same time. But the programs we write have to be made in such a way that it can actually do that, and that is hard in some cases. Another nice thing about concurrency is that you can write applications that do something else while they're waiting for something. So if you talk to an external API or have a database or have a file system where you need to access a large file, then you can do something in the background as well. So not your whole program blocks when you're doing some heavy task. However, in most other programming languages, concurrency is considered a very hard problem to solve. It's very hard to use it. And why actually is that so? I can give you a very quick example of the way that this works in most other languages. Again, it's hard because multiple things happen at the same time, and you're not always entirely sure in what order they then will happen. And when they're using the same information, the same memory, things will often go wrong. Here's an example. Say we have two threads, two concurrent computations going on side by side, and we have some memory. And thread A reads something from the memory, and then starts computing something with that value. However, in the meantime, thread B also reads something from the same memory and starts another computation all of its own. Thread A is now finished and puts its result back in the same memory position, and thread B is after that also finished and puts its result back in the same memory position. But now we have a problem because we've lost some information here. One of the two computations we did has been lost, and this makes it impossible to reason about our programs, and it makes it very hard to do garbage collection correctly, and there are going to be all things going wrong and crashes happening. And so this is really a problem, and these kinds of problems are called race conditions, and other languages try to solve them by introducing things like locks or mutexes or atomic variables, but they don't really solve the problem. They mostly say, well, this part of the program can't actually be concurrent, or you can't access this part of the data while something else is accessing it, which brings a whole set of new problems with them, which are therefore not really a good solution. The actual real good solution is to say, well, just never share any memory, never share any data between threads and have them access it at the same time. So this is the idea that Elixir and Erlang took, and this approach is what is called the actor model. It has basically three rules. The first rule is we have processes, and these are very lightweight threads, and every process has its own isolated memory. It means that only this process can access this memory, and the process is the only thing that itself can take care of the memory. But we want, of course, talk to other processes and have to be sure that we can do that. So the only way to pass information from one process to another is by sending that process a message. And also, it is possible to create new processes whenever it's necessary. And this means that when you need more, or when a process has quit and you need another one, you can always start new ones to do a certain task. These things are done for you by the virtual machine, which means that we are sure that there are no exceptions to these rules. And this means that garbage collection becomes a lot easier, and we can be sure that there are no strange crashes happening. And this means that we can actually write programs that really run concurrently. So the virtual machine of Elixir has a scheduler that really distributes your program between multiple cores of your CPU. Other languages, such as Ruby and Node that Rico talked about in his talk, they are unable to do that. They introduce something called the global interpreter lock, which basically means we show you something that looks like threads, but in practice, because we are not sure that we will always be able to access this memory that was there before, in the end, it will only run on one computer core. So by not having that, by being sure that we can actually only access the memory from a single process, we are sure that we can actually do multiple things at the same time. And this is what makes Elixir so much faster when doing concurrent applications. All right. So this means that the actor model is possible to truly run code at the same time. It also means that it's possible to have multiple computers which both have some processes in them and just pass messages between those. And in Elixir, this works exactly the same as when you were passing messages between local processes. And the cool thing about this is that you can even write applications that run on multiple computers, and when one of your computers crashes or there's a hardware failure or a power outage, then your application will still continue to work without any problems. And this is how the Erlang, they managed to get this 9 nines availability. And this also, of course, has to do with fault tolerance, both on the hardware and the software level. Basically, when one process or multiple processes that are linked together go down, then the rest of the system can just continue on like nothing happened because there's no shared state between them. Programming in this style can be compared with programming for an ant colony, because we have all these small workers that do something, and we basically describe the way they are interacting with each other. And when one ant dies, we can just send 10 more at the problem, and then it will probably be solved. So this is what a process looks like symbolically in Elixir. It has its own data, which only itself can access. It knows itself what it's doing at this time, and that might, of course, change. So it knows where it is in the program. And it has its own mailbox, which it can read when it gets messages from other processes. So when we send a message to another process, that looks a bit like this. So at some point, the computation in process A decides it has some data that might be interesting for process B, and then it sends a message over there to process B's mailbox. So an Elixir application can, from afar, look a bit like this. We have many processes going on and many messages passing around, and these processes are so lightweight that you can easily start tens of thousands or hundreds of thousands on a normal laptop, which really makes sure that you can create really cool things with them. So a process has two important things. The first is its so-called process ID, which is basically the address you can use to send messages to. A process can send messages to other processes, but there's nothing wrong with sending a message to yourself, which you might then use later. And then it also, of course, has the mailbox, and when a process decides to read a message from its mailbox, then it first reads the oldest message, and this ensures that it's very easy to reason about what's actually going on, because you know in what order messages will be read when they come in. So when we start a process, it does something, and it might send some messages to other processes or start more processes, and maybe it terminates. And after it's finished doing some things, it's going to wait until it receives a message, and then it starts doing something again depending on the contents of the message, and this continues on. And the scheduler of the virtual machine can divide how these processes are spread out on the multiple cores of your computer, and when one process isn't doing anything at a time, then another process can take over, and it really looks like all of them are actually going on at once, which is really nice. So in Elixir, we have 4 basic building blocks to create to do these things, and these are built into the language. The first one is called self, which returns the address of our current process. When you start a program, you always start with a single process, which can then spawn more processes. Spawn is a function that spawns a new process, and you can pass it spawn itself a function, which is then the code that will be executed on that process. And we have send, which takes a process PID, so a process ID, and a message, and message can really be any value, and then the current process sends this message to that process. And we also have receive, which blocks the process and waits until there's a message. If there already is a message, it just reads the first message that's already there. If there isn't any message, it will wait. And you can optionally also pass some extra options to receive that says, well, if we don't receive a message in this time interval, we continue doing something else. So here's a very basic example of multi-process, so concurrent code in Elixir. We spawn at the top lines, we spawn another process. This process has a very simple function. The only thing it does is wait until it receives a message. This message contains both a sender and contents, which this is the message that we will try to send it. And the nice thing about passing it the sender is that we can then send something back. So we send to the sender a reply, which tells the sender what kind of message is sent in this case. So, and then we send this other process a message, and after that, in the main process, we have a receive block as well, where we just wait for any message at all and put this out to the console. So this is of course very nice, but you really want to see how this will work in practice. So let me start up a terminal here. Hi everyone, now you're able to see my face. Here is a terminal. Yes, I think it works. Great. So here we are. And this is exactly the example I've shown in the slides. And we can now simply run this using Elixir. So this we do by calling Elixir run the basic example. And as you see, in the end, the main process receives a message and it decides to output the contents of that message, which include the original message it sent itself. So this is a very, very basic example. But these are the basic building blocks in Elixir that all concurrent applications are then built on. So let me continue with the presentation. Here we are back at the slide with a code example. So this is really nice. These 4 building blocks do everything for us, but it gets you quickly start writing very long code, very repetitive code, because these kinds of statements are very common and these kinds of patterns are very common. So what the people of Erlang, Ericsson, the company that created Erlang, realized early on, yes, is that they were able to get all these patterns and write a library that implemented all these common patterns, so you wouldn't have to write them over and over again yourself. And this they called Open OTP, and OTP is short for Open Telecom Platform. And telecommunication with telephones is of course what Ericsson originally did, but telecommunication is actually a bit of a broader term, meaning any kind of message passing in an electronic way between entities. So in that way, the name OTP is still relevant today, although most people always abbreviate it and don't use the full name. So OTP is a library. It's basically part of the standard library, the built-in library in Erlang and Elixir, and it contains many tools that make it easier to work with multiple processes and concurrent applications. So the boilerplate that you need is reduced a lot. It becomes a lot easier to send and receive messages between different processes. OTP also introduces blueprints for many kinds of processes, many kinds of patterns that you often need, which also really reduce the amount of code that you need. The cool thing about this is also that it adds synchronous message passing, the normal low-level message passing is always asynchronous. That is, I send you a message and maybe at some later time you send me a message. And synchronous message passing means that I send you a message and then I wait until I receive a reply. And when I don't get a reply during some specified time, then I decide that I've waited too long and I crash myself as well as the other process, which makes sure that nothing hangs in your system. So this is really nice that you can also just pass things synchronously, call things on other processes synchronously and have the code work sequentially whenever that's needed. OTP also introduces ways you can supervise processes, and we will go into more detail about that in a little bit. It also adds the possibility to register names, so you don't have to pass the process IDs around everywhere in your application. If you have a single process that does a single task, you can just give it a name and refer to that name in other places of your application. It also has some very cool debugging tools such as Observer, which I'm going to show you a little bit later on as well, which make it really easy to work with multiple processes. There are also some more advanced features built into OTP, such as the possibility to reload part or upgrade part of your application while it is running, and also the possibility to create really distributed apps where if one computer crashes, the others just take over. So the most important aspect of OTP is its generic blueprints, or behaviors as they're also called in Elixirs. And there are basically three kinds in Elixir. You can use agents, which are just a process that wraps around state. So you can give some state, some values to the agent, and then it remembers it. And then later you ask the agent, hey, what did I send you? And then it sends you back those values. Agents are really nice when you just have some state that you want to keep for later. And otherwise, there are other things you can use instead of agents. We have tasks. These are basically meant to easily parallelize something, some kind of computation where we don't have a lot of message passing, but we just want to do it side by side. So yeah, tasks are not built to do a lot of message passing, but are really easy to start and stop without extra boilerplate. And finally, the generic server, and this is what agent and task are both built on top of. And this is when you're starting to create a little bit more complex applications. This is what you will use most of the time. And a gen server allows you to initialize the process in a customizable way, and it allows both synchronous and asynchronous message passing. It also allows you to do cleanup when the server dies or decides to terminate. And there are some other things also built on top of gen server, but these are used a lot less frequently, and I won't be covering them in this talk. So when you're using generic servers, this is basically what is going on underwater. You call genserver.start from somewhere in your application, and then the internal code of OTP decides to initialize a new process. Then it calls your custom-defined init function, if you have one. If you don't, then simply nothing happens, and then it goes on and waits for messages. And you can then use genserver.cast, genserver.call, or just the bare bones low-level send, and these will be handled by the genserver code, and the callbacks that you might have defined, handle cast, handle call, and handle info, respectively, will then be called with whatever message went in, and also some extra metadata, such as the process that sent the message, which makes it very easy to return messages. And these callbacks that you define also get past the current state of the process, and when you finish those callback functions, you can write the new state and also possibly the reply to the caller process. So in that way, you can completely define the behavior that's going on underwater in your gen server. All these callbacks, I hope you can see my mouse cursor, by the way. I'm not sure, but I hope so. So all the callbacks at the right side are things you might define in your own module, your own application for this specific kind of thing you want to do. And if you don't define one of these, that's not a problem at all, because in that case, simply nothing happens. And that's the way Gen Server works. So again, I'm not going into the syntax, deep into the syntax here, but that is the basic idea of how these behaviors, these blueprints work. So let us move on to a practical example which we want to build using this style of programming and also leveraging OTP. And the practical example I chose for this talk is building a high scores table. And why did I choose this kind of example? I chose it because I think it's easy to understand. And also, it's something that is not as trivial as that you would just be able to fix it in 1 or 2 lines. So we actually have something to talk about for a little bit. And maybe the most importantly, it is not a to-do list. Most of the other introductions or tutorials on concurrency in Elixir or also other languages for some reason always talk about to-do lists or bucket lists of some kind, and I wanted to do something different. So, high score tables. Well, what is the idea of a high score table? We have a nice picture here of Pac-Man, and the idea is when someone has played a game, we want to save their score into the table, and when someone then asks for the score, we want to be able to return all the scores. So we want to know for the top 10 or maybe the top 20, this might depend on the specific game we are using. We want to store all the scores of those players. And each of these scores should have the player name that achieved that score, the actual score, and for nicety's sake, let us also store the moment at which that score was achieved. And then we also want to return the current table whenever someone asks for it. So when we actually try to implement this using OTP, we will use a Gen server for it. Just the agent is not enough because we want to do some computation when we receive data, and because not always we will add new scores to the table, but only if there is room and the score is high enough. We're also not going to use a task because we do have to keep track of the current state of the table. So it's not just a computation, so we use a Gen server. So it has internal state, both a list of scores, which is the most easy way to store this, and we also want to keep track of how long this table should be, so how many players we should keep track of at a single time. So when we initialize the Gen server, we should pass it how many players we should keep track of for the single game, and then when someone adds a score, we try to add that score, but if it might fail, and in that case we return unfortunate, and in the case we actually manage to add that score to the table successfully, we return a tuple containing congratulations and the position the player actually got. And finally, we also want to return the current state of the table, so we have a method that does that as well. These are the things that we are going to implement on a Gen server. And let me show you how this will look. So I have the code here as well, but this is a little bit hard to see probably, so let me fire up my text editor. So here we go. I think, yes, you can now see my Sublime. So this is what the module will in the end look like. We define a module which we call high score table. We say we want to use the generic server, which means that all these default versions of the different callbacks we might create are defined for us, and if we don't override them, those are used. We need some kind of way to store the MP scores, and we also want to keep track of the maximum amount of players. a single score, we want to store that as well, which we can easily do with a struct. And then this is really where things are going to happen. This top part is where we, these are the things that other modules, so other parts of a program will call whenever they want to talk to a high scores table. And this bottom part is what actually is called internally by the gen server behavior whenever some of these top things are used. So this is very simple. We can pass start link an amount of players, and then gen server will start it, and this will call the initialize method down here.
Excuse me. The text is too small for the projector.
All right. I can zoom in a little bit. Is this better?
No. Thank you.
More.
All right. Very well. Sorry, I should have asked and should have thought about it. So I hope it is readable now. So here in the top we say
a little more.
All right, let me continue. So here in the top we use gen server, and then we have these structs that define the code, and then we can start this high scores table, and after that we can add a score to it.
Sorry, can I ask to zoom it a little bit more?
Even more? Yes.
Yeah.
Is it readable like this?
Yep.
All right. That's better.
Yeah.
Thank you.
Okay. Great. And here are the two things we can do. We can add a score to the to the high scores table, and we can ask it for the current scores. So when we add a score, we take the current time, we wrap the current score in a score struct, and then we say, hey, this is the score we want to add. And what then happens is that we check if we are able to add that score to the table, and this creates a new state for a gen server. This is already quite a bit of code, and it's not a problem at all if you don't understand exactly what is going on, because again, this is a lot of syntax, and I don't want to go into too much detail about the syntax. But I can show you that this works properly. So let me go back to my terminal. Here we are. Let me zoom in a little bit as well here, by the way.
Okay. Is that better?
Yes.
Everyone, is this better?
Yeah.
Or do you want it to zoom it?
It's fine.
All right, it's fine.
All right. So this is better. Is this readable like this? All right. So here is again the. This is the code we were just looking at in Sublime, and we can start this up using the Elixir interpreter shell. So we can first start our high scores table. And say we want to keep track of 5 players for this specific example game. So now we have its process ID here, and we can use that to pass messages to. So we can now say, well, we want of this high scores table to store to add a score. Because someone achieved the score 5. So I have 5 points, so I want to add that to the high scores table. Of course, before this it was empty, so yes, I'm now in first place in the high scores table. When someone else achieves 4 points, then they will become second in the table. But when someone has more points than the first one in place, then they will become first again. So we can also look at the current state of the table like this. Of course, I have to pass it the process ID as well, and these are the scores right now in there. So we can continue on like this. Say there are some more scores. Now the table is full, and as you can see, if the score is too low, it won't be added anymore. And this is the final state of the table. So that is a very a basic example of how a gen server works. This is nice, but yeah, it's already quite a bit of code for this small example. And well, how can we enhance this further? How can we make this work when we have multiple games? So that is what I'm going to talk about next. So let me start up my presentation again. And now I can screen share the presentation. Here we are. All right, so this example works, but this is just for a single game, and it is still quite a hassle to pass this process ID around and to make sure that everything works right. And we still are missing some things because it isn't really fault tolerant, because, well, if the high scores table fails, then it just fails and we don't really know what's going on in the rest of our application. And when we want to have multiple games, then we also have a problem because, well, yeah, we have all these things side by side, but how do we know which high scores table we actually want to talk to? And these things can be solved by introducing supervision and crash handling, which is one of the other parts that are built into OTP. So to make our application scale is actually relatively simple. We just need more processes which do either the same task or some new tasks that work together with the things we already did. But yeah, this introduces new problems because some of these might fail at some times. So we also need fault tolerancy. And that means that we want processes to be able to keep track of other processes. And when one of the processes dies that does some important work, we want to know that that happened, and we want to be able to restart them. So in Elixir, to keep track of processes and to be able to restart them, we use things called monitors and links. The idea behind these is simple. So we have crash handling in monitors and links. The idea behind monitors is simple. You register with the virtual machine, hey, I want to monitor the other process, and here's its PID. And now if that process dies, then a message is sent to me. So when A monitors B, when B then dies, then A receives a message. Monitors are one way, which means that when A dies, nothing happens. Besides monitors, it's also possible to use links, which is really useful if both processes depend on each other. When a process is linked to another process, this simply means that if one of these dies, then the other dies as well. And finally, this is the half extra kind, is when one of these processes decides it wants to start trapping exits. And basically what this means is that they get out of this contract with the dev. So when, in this case, when A is trapping exits, then when B dies, A is notified, but when A dies, B is notified. And this final version is really useful if B should be terminated when A is terminated, but when it's the other way around, we only want to get a message. And this is, for instance, the case when we are using hierarchies of structures. So when we have a tree of things with parents and children, or with supervisors, which is the next thing. When something breaks, we want to be able to know that it happened, and then we want to be able to restart it. And this is called supervision. So we have some processes in application which we call workers, which basically do the work. They do the things we want to be done. But we have other processes the supervisors. And these just look at the workers and see if they're still working properly. And they might also supervise other supervisors as well. And supervisors might start workers or restart workers when something goes wrong. And when too much goes wrong in a short time, they themselves decide, wait, this is not right. I don't know what's happening here. Clearly, when I restart my workers, I don't fix the problem. So the problem has to be elsewhere, and then they crash themselves. This how this exactly works is fully customizable because it's very your application specific. So Elixir comes with different supervision strategies, which is, well, what other workers of the supervisor should be restarted when one of them fails, and also how many things can fail before this supervisor decides that it's too much and it should crash itself. So we have these supervision strategies, which humorously are more or less all named after the Three Musketeers things. We have the most simple one, one for one, which is basically when a worker dies, it itself is restarted. This is fine for many cases, but in some cases a process is actually, so more workers are dependent on each other. So we also have one for all, which means that when one worker dies, all of the workers of the supervisor are restarted at the same time. And finally, there's rest for one, which means that if one dies, then all of them that are newer than that one are terminated and then restarted. This is used a lot less, but is useful if your workers are in some kind of a chain computation with each other. Then there is more or less an exception called simple one for one, and this is a bit different than the others because the other kind of supervision strategies, the other kind of supervisors can take any kind of worker processes. Simple one for one can only have workers of a single type, and it starts empty, and then dynamically workers can be added and removed. And it is mainly useful if you don't know how many workers you're going to need at a certain place, and when it's more important for you that the works are removed when the whole, when other parts of the application have crashed, because most of the time when you're using dynamic workers, you don't really want or need to restart them when they die themselves. So finally, we have something called supervision trees. This, because as I said earlier, supervisors can supervise workers, but they can also supervise other supervisors. And programming concurrently in Elixir mostly boils down to how am I going to structure my supervision trees to solve my problem in a proper way. And the nice thing about structuring your application in this kind of shape means that it's very easy to see what parts of your program talk to each other, and also what parts of your program will break when other things in your program will break. So the idea is very simple. We have, when we do this, multiple layers of fault tolerance, and it also means that when something breaks, then everything that depends on that is also terminated, which ensures that we don't have things like memory leaks. So a very basic example is we have a supervisor and it has multiple workers. Now this is a nice, very simple application, but at some point we might want to add another process which distributes the work that is coming in between the different workers. So we add another process, in this case called a pool server, which receives work and distributes it, and we add another supervisor on top. So now we have two layers of supervision in our supervision tree. And when one of the workers dies, that's not a problem. We can just restart that worker. But if the pool server dies, well, then we should just restart both the pool server and all the workers, because whatever was going on clearly was broken in a large way. So when we have a thing like this and we want to have multiple, in this case, pools going on at the same time, we can wrap this whole thing in something we call a pool and basically add just another supervisor layer on top of this again. And now we can have multiple of these pool supervisors side by side and have this root supervisor on top and start and stop them at will. And if we want, we can go and stack more and more layers on top of this. At most of the supervision, ways of supervision, most of the applications in Elixir actually form this kind of pattern in their structure. So when you have data, this data actually isn't coming from the supervisors, it's coming from the side. Because most of the time it is better if your supervision processes only handle the what should happen if things crash part and have your data flow happen elsewhere. So this is basically how such an application would look. And this is only one example, but we can easily change this to something else. In this kind, now the names have been changed, and now we're talking about something that listens for requests on an internet port. And this kind of, so what I'm here calling a socket pool, this is basically what happens inside applications such as Phoenix, where they are able to have many connections side by side, because a new request comes in and the socket listener decides, oh, we need a new connection, and then this connection is made, and then this connection can call other parts of the application. So this is very generally can be used in many different kinds of applications, this kind of structure. Finally, when I talk about application, when we talk about applications in the Elixir world, this is basically a wrapper around all of this. So when we have a whole supervision tree, we want to package it, and we want to package it as a whole. This is what is called an application. So you might actually, when you have some project you've written in Elixir, you might have many applications running at the same time. All your dependencies are an application. And the cool part about this is that Elixir has built-in ways to easily start and stop these applications at runtime without stopping your whole project. And this means that you can also update them one by one. And you can configure them one by one. And you can easily reuse them in other systems, in other packages, other libraries. And this really means that you can easily reuse the same code, the same programming things at multiple locations. So let us go back. Oh yeah, one final thing is we can use Observer here to very easily debug this. And I'm going to show you this very soon. Let us go back to our nice practical example with the high scores table. So we want to have multiple games running at the same time. So down here at the bottom we have the old high scores tables, and they are completely unchanged from the version you saw before in action. But now we've added a few things on top. We have a supervisor, which ensures that we can have multiple of these things running side by side. And we have this thing, a high scores registry, which basically lets you start one of these and at a later time, and it decides what game actually is managed by what process. So people that are storing a new score or asking for the score of a certain game don't have to handle process IDs anymore. They can just pass in a name to this high scores registry. And you can also add new games at will. So now the code becomes a little bit larger again. This bottom part is exactly the same code as I've shown you before. Then we have the high scores registry, which is here circled in red. This code is probably in the presentation also too small for you to see. I'm going to show you this in my text editor as well, because then it will be easier. And then we have the supervisor, and finally the root level supervisor, which is the application. And this is then the whole application in together. So back to the text editor. Can you already? Yes, I'm sharing the text editor. Great. So this final application looks like this. We have the high scores table. This is exactly the same file as we had before. Then we have its supervisor, which is very short. It just says, well, when we start this, we want to start it as a supervisor. We have only one kind of children, namely the thing defined in this module we already had. And we want to supervise it with a simple one-for-one strategy because we want to start and restart them whenever we want. We don't know how many games we already have at the start. And then we have the registry, which can be started, and it itself is just a gen server. So when it is started, it gets initialized with just an empty map. And then people can add a new game, add a new score, add the current scores, and what this does is first just look up what game it is, and then call the function we already had defined in the other method, in the other module. And the same for listing the current scores. It's also just looking up what game we're talking about and then returning the result of that other function. So how to find out what process we're actually talking about? For that, we look in our list of games, so our map of games for the game of the specific name. And then we see if we get back a PID. If so, then we return that, and otherwise we return an error saying we don't know what game you're talking about. This final part here, this is a method that is called whenever one of the high scores table processes dies. This is because we monitor them, and this ensures that when that happens, we start a new high scores table for that specific game. I will show you what happens when this is actually executed by just killing off some high scores table now in the live demonstration. So let's go back to the terminal. Here we are again with the terminal. So now we start up our complete OTP application. Right now, because now it's an application. I hope this is big enough, by the way, for the for your beamer. We can see here what is going on in this tab here, listing applications. What you see here is the supervision tree that we're using for this specific thing. So we have the registry here, we have the supervisor here. We don't have any high score tables yet, and the root supervisor is here. So we can now ask this high scores registry to add a new game. And because we already have it, we don't have to, and we gave it the name, we don't have to. Because it's already started, we don't have to start it ourselves again. So we can just use it like this. We add a new game, say we add chess, and then it returns OK, so because we've added this game. And we can add another game, say tower defense, and we add it as well. I just realized that you can't actually see the server screen. Okay, let me share my whole screen for a moment. Okay, now to the right you see. Okay, wait, let me try it again. Doing things live is always so much fun. Can I see this? Yes, here we go. This is the observer window, which you get when you use observer.start from the Elixir shell. So here we have the supervision tree we just made. And these are the two tables we just started. And this is the registry, and these three things have already been started for us when Elixir started up. So because we now have this fault tolerance inside, we can just say we want to kill one of these processes. Yes, I want to kill it. And now, boom, we have new processes in its place. So that's really nice. So to let you, let me go back to the terminal. So we have added a few games, and now we can high scores. Add a score to a certain game. And say we add another score, and then we can again check current scores. One of these games. So now you see that these scores, two scores, were saved over there. So this is really nice, and we can now add as many games as we want, and everything will still work. And we might also, we can expand this further and use some other kind of data store, and we might be able to distribute these different high scores tables on multiple computers and have everything work exactly the same way as it is now. And so yeah, we can take this even further, but this is as far as we're going in this talk. So let me start up the presentation for the final few slides. So this is the example, and I think it's very neat. But of course, you can even go even further. You can name your processes using a tool called PG2, which makes it even easier to use multiple processes and to use the registry. You can use ETS, which is basically a built-in database layer, so you can just store information and retrieve them from other processes without calling them all the time. You can also reduce much of the boilerplate we are still having currently by using a project called Xactor, which is a library built on top of Elixir. And it might also be possible to have a single game on multiple computers and distribute calls to it, which might be the case when, say, we have millions of players of our nice tower defense clone, and we want to store the score, but it would be too expensive to look up the score at one place, so we could store it at multiple places at once, and then the lookups all can happen at a single server. So these are some ideas, and the conclusions I want to get from this is that it is possible to build applications that are concurrent in Elixir, and it works a lot better than the concurrency in most other languages. And yeah, you can build things that are scalable, and that is really nice. And there are many built-in tools in Elixir that make it easy to build these kinds of things, and that also make it relatively easy to still understand what's going on at all times. And you can go a lot further with this, and your code will be relatively maintainable in relation to other projects that use concurrency. And it's very easy to reuse things you've built before. So the final conclusion is Elixir is a really nice tool, and I hope to have informed you a little bit more about how you can use Elixir maybe to solve your specific problems. And of course, in the end, use the right tool for the right job. But I hope you're now able to consider when Elixir would be a good tool to use for your specific problem a little bit better. So in the end, I think if you know what different kinds of things there are, then a winner really is you. There are some other things you can look at if you want to know more. There is a great book called Elixir in Action, which goes into a lot deeper detail than I did here. There's a great book called Lyris on Erlang if you want to look more into the Erlang stuff. Some of the diagrams in this presentation have been adapted from one of these two books. There's a great documentation on everything that was going on here, and it includes great examples of the syntax. And there's also this great talk by Sasha Jurik about discovering processes, which goes into a lot more detail. So, and with that, we're finally at the end of this presentation. I want to thank you very much for your time, and I hope it was, I hope you've learned something, and it's been a pleasure. Thank you.